good dots?
Chlorine.
Chlorines, why not hydrogens? Okay, did you, before we started this, what did you do? How many valence electrons are there? 20. And I've reinforced that with my honors kids today. We're almost doing exactly the same thing. We're just at a different level than them. If you help them, you best make them count those valence electrons, okay? Because they will just start drawing, and then they'll have no idea if they had to check themselves, okay? 20 valence electrons, bond, 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 bond. Hydrogen, how did you guys add where did you add your ligands? What was your placement? So you put hydrogens on opposites, okay? And you put chlorine top and bottom, some of us. Does it matter?
No.
No? Okay. You added your electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, done. Geometry? Tetra. Okay, and that's molecular group, or molecular geometry and electron group, because there's no additional lone pairs in the central atom to cause any discrepancies. Bond angle? 109.5. Polar molecule or non-polar molecule?
Polar.
Raise your hand if you say polar. Raise your hand if you say non-polar. Why non-polar? Who cancels each other out? The CLs? Why? Well, that's how you told me to draw it. I just drew it that way because you said to draw it that way. Why couldn't I do it this way? As you said, it doesn't matter, right?
No, yeah, it does because those are.
Isn't this just as valid as that?
No,
Yeah.
I mean,
What creates a validity here? It's not resonance. Resonance would be a double bond or triple bonding in resonance. This is not even an isomer. This is the same dang structure as that. Build it right now. You have a minute. Build it. It's okay. Those are my AP kids. Use it. Just use it. It's a single bond. Carbon is black and chlorines are green and hydrogens are white. Carbon is black, chlorines are green, hydrogens are white.
We don't have any green ones.
Those are greens. And I want you to discuss in your group to just polar and non-polar.
Or no, AJ, do these cancel out? Tell me, do these cancel out? Do they cancel out? So why would you see that more?
So we have this built, right?
Yeah.
It doesn't matter how I hold it, how I draw it. There's an unequal distribution of electrons here. Where are the majority of the electrons, and how does the bond polarity point to that? So the green ones are chlorines, right? That's more electronegative than carbon. So carbon's pushing its bonded pair of electrons, pushing them towards chlorine, and then even hydrogen, who's more electronegative, hydrogen or carbon? Carbon. So then even from that aspect, it should make sense. Hydrogen's pushing its electrons towards carbon, There's a big shift of electrons up, lack of electrons down below on the south side here. So we have a huge dipole moment pointing up on this molecule, no matter how you think about it. We have a polar molecule. So even if you draw it one way, do not trust your drawing. You need to visualize it, because you don't get to build it all the time. And on organic chemistry, I got a kit, I could build on tests, but it wasted my time. But we would build structures that were 20 carbons long, right? So you need to be able to visualize how this doesn't matter where you place it. But that's a 2D structure. Yes, of course it looks like it cancels, but it doesn't. That's a 2D structure. You can definitely tell it looks as if it's polar because there's an unequal distribution of electrical charge. Okay, so don't fool yourself in thinking that your drawing is perfected. Because you need to consider the different range codes that it's taken. Okay, so that's certainly a polar molecule. And my polar molecule has what IMF? What IMF? Intermolecular force. Dipole. Why not hydrogen bonding? There's no hydrogen bonded to. Hydrogen bonding to
oxygen, phosphorus, and nitrogen.
Fine. FON. Fluorine, oxygen, nitrogen. Okay. Now textbook homework from yesterday. Okay, back to me. Deconstruct. Back to me. Alright, so So I wanted to answer a couple of the questions that were the even ones, because I knew that you guys can check those in the back of your book. You need to practice your polarity a little bit more, but I'm hoping that I can get feedback from your labs. So that's my goal for tonight if I can. So this was our structure that was indicating the difference in length and strength between nitrogen to nitrogen based on the structures. I didn't see very many structures drawn. Draw the Ding-Lewis structure, or you're going to get it wrong. I almost guarantee it. You just haven't drawn them enough to know them. So some of you guys can visualize very, very well. I do try to support yourself in drawing Lewis structures. So we have our octet achieved, we have a single bond, we have a double bond. Double bonds are certainly shorter and stronger. So N2H2 should be shorter and stronger in N bond, nitrogen to nitrogen bond. Questions there? And I'm an adult, but I'm still counting my electrons because I know that's how I have to check. Okay, so do that for yourself as well. The 35, these are the ones that asked about kind of the whole picture, structure, shape, bond angle, and I thought I asked for polarity. Did I have polarity on there? No, I don't think I'll go over polarity as we go though. So in this one you have, what's PF3? Name?
Phosphorus trifluoride.
Trifluoride, okay. You have a molecular geometry of what? Yeah, lone pair, 3 ligands. Trigonal. So just trigonal pyramidal. Okay, and then it was 109.5, but now it deviates from that angle because of what? The electron lone pair, and so we can say it's 107. Look on the sheet I just gave you. This is from, I thought this would be helpful for my people still struggling with bond angles. The ones I'll highlight are the ones we're doing as we go. So it says pyramidal. It doesn't say trigonal pyramidal, but you see the difference there. It says less than 109.5. So that's a way you can describe it. On your AP exam, they'll take that. They'll also take 107. They just know it's not 109.5, right? Because that's our tetrahedral appearance. No lone pairs to cause any distortion effect or cause any deviation from our normal. That's a way that it'll describe it as well. What creates the deviation? The lone pair repelling it. And then electron group geometry is definitely tetrahedral. All right. So then we have SBR2, name it. Sulfur dibromide. I know we don't name things as often as we used to. Sulfur dibromide. We had 20 electrons, added them all on there. What's this shape the way I've drawn it? Oops. Sorry. Look how I've drawn it. I've drawn it straight, but does it mean it's linear? No, because what's happening to the lone pairs? Where do they look? Like, think about your tetrahedral geometry. Where do they go? Is there really a top, bottom, side to side?
No.
Not really. It's a 3D shape. So they kind of take like the top areas, and the 2 bromides take the bottom areas. So the lone pairs are pushing on the bonded pairs to create that bent shape. So I was thinking like Mickey Mouse ears is where they take. Yeah.
So is it like all of the lone pairs on the top sides kind of like cancel each other out by pressing against each other, and then they're just the 2 lone pairs on the sides pushing it in?
Whoa. Are you talking about sulfur or bromines?
Like the bromines.
Don't look at bromines. That's a point. Let me make that now. The arrangement of our geometry is always focused in on the central atom. We look at the geometry around the central atom. So we don't even include the lone pair on the outside ligands into our discussion. We look at lone pairs on the central atom to see how it distorts the geometry, and that's it. That will help focus your talk here. Let me get your question in a second. Yeah?
Wait, so both lone pairs are on the top like sulfur?
Or both on the bottom, but they're on the same side. Build it. Go ahead. Take 30 seconds. You guys have the structure in front of you. You need to find an atom with four poles. I think it's the black one. I'm really trying to do my best to have you visualize these because you won't get these structures. You won't get them. There is no arrangement for the lone pairs to cancel each other out at all on a tetrahedral geometry. You must remember it's not north, south, east, west. It's a 3D structure. There's no way to allow for lone pairs to cancel each other out. What? You can keep rearranging your ligands, and there's no way. It will always be bent. It will always have lone pairs on one side. Does that make sense? So we draw tetrahedral like a cross, because that's how we symmetrically distribute it we show it on a 2D structure. But as I saw some of you guys yesterday, if I find my marker, you guys were doing a good job of trying your darndest to say, okay, I can't think 2D, I have to think 3D. And you drew like a little hydrogen, and then a hydrogen, and then you drew like a little kickstand out for your chlorine, to say it's coming out of the board, and then you put a chlorine back into the board to try to simulate that 3D structure. And that's how you draw it in organic chemistry in college. So if you want to start now, go ahead. But it's supposed to indicate 3D, so to me that's like, heck yeah, these chlorines are going to cancel each other out, and there's no chance of it being non-polar, that's a polar structure. So keep thinking about that tetrahedral arrangement, how it doesn't cancel each other out. All right, so it's bent. 1 and 9.5 is caused by the distortion effect of the lone pairs. Yes?
There's 3 lone pairs.
Yeah, it is. That's only if it's 3 lone pairs and there's a single. How many lone pairs are there? No, you had the wrong middle atom. How many holes are open there? Yeah, you have the wrong. Choose. So this has sulfur has how many electron domains? Everybody. 4 electron domains. 2 are bonded, 2 are lone pairs. You need to have the choose one of 4 electron domains. I think is the black colored bead. Okay. Sometimes we have sulfurs that can expand octet, which is why the purple has 5. Yeah. So not every color coding thing works for every single atom. That's what I'm just trying to tell you. 4 electron domains. Okay. All right. So distortion effect by lone pairs. This is Oops. Somehow I missed. Okay. Trichloromethane, so we have 3 chlorines, 1 hydrogen. That's an obvious what kind of polarity? So certainly polar. There's no chance of any kind of equal distribution of that. We have a very large area of negative pushing of electrons outward. So it's partially negative here, partially positive here, polar molecule. I didn't do the polarity up here. What's the polarity of sulfur dibromide? Question? Polar. Okay, because it's not linear, it's bent. There's 2 lone pairs up here. The bromines are down here. Sulfur here. You have a huge partial negative region on top and a possibly partial negative on the bottom with the bromines, but not nearly as magnitude of the lone pair. So this is that bent shape creates the polar attitude overall. Yeah. No. If I have this, all the same ligands, nonpolar, because there's no area where there's an unequal distribution of charge. Because over across the board on that tetrahedron, these are dipole moments that point towards the carbon, because carbon's more electronegative than hydrogen. So this would be partial positive all the way around my globe. So that would be overall equal distribution of charge, nonpolar. Same story if I had carbon tetrachloride, 4 chlorines around, there's no unequal distribution of charge because all of them have a partial negative. So it really helps if they're the same ligand because then they're all going to cancel each other out basically. Yeah. Shortly? Yeah. Okay. So that would be carbon dioxide would be a great example of that. So I can show that in a second. So in this example that we're here on, this is tetrahedral, no cancellation can occur, polar overall. There is no deviation, it's 1 in 9.5. So 51, a bunch of you guys said I didn't know how to do, so I'm going to talk about that one first. These were determining if it was polar or non-polar, so I've drawn the structures for you as well. So chlorate, we have our negative charge overall. We do have to put the brackets there with the negative charge on the outside to indicate this is a polyatomic ion. And then there are 26 electrons in our structure. What's our overall shape here? Yeah, trigonal pyramidal. What's our electron group geometry? Tetrahedral. So chlorine is able to expand octet. Okay, chlorine is our PCl-AR. They can expand octet. So overall, though, because it's like this, kind of a triangle with a lone pair on top. The lone pair is huge and it's taking up a lot of space. It's repelling down, creates that triangle appearance. And despite these being partially negative with the oxygens, actually not alive, you'd have to fight me on that one. Oxygen might be more electronegative than chlorine because they're really close together, but you don't actually have to really think about too hard about that because even if these are partially negative or partially positive, the lone pair has a huge partial negative, so there's a definite magnitude difference there. And that magnitude difference creates an unequal distribution of electrons, hence, or electrical charge, hence a polar molecule, because of the geometry. See confused faces. Can you agree with me? Yay, nay? Yeah.
Eric, when I was asking history about like the double bonds, like for example, in that one, if you take away the double bonds, like and they're just single bonds, like does that change the electronegativity? Or like the polarity?
It does not change the electronegativity or the polarity, because the difference between the nuclei are really what the electronegativity plays into. I chose to do that way because of the formal charge. Because I needed oxygen to have, if possible, a formal charge of 0. And if I put single bonds there and lone pairs out, we'd have -1, -1, -1 formal charges, and chlorine would have had a +2 formal charge, and that's way too many charges for formal charges. We want zeros. So that's why I went double bonds on that one. So the formal charge helps you to determine the best fluid dot structure. Okay. And then this one, sulfur dichloride. This one had resonance to it because you had the ability to put the lone pair on either side. But in both cases, there's a lone pair on our sulfur. So overall, our shape is what? Jack, will you shut my door? What's the shape? And I'm drawing it one way because that's when you start drawing it, you don't know the shape off the bat half the time. So you probably just draw it linear. But it's not linear. You have to consider how the sulfur's lone pair creates that repulsion which bends the structure like that. So it certainly is bent, and if it's bent and there's a big, huge lone pair on top, it's certainly polar as well, because there's no ability to cancel dipole moments. If it were linear, and your dipole moments are pointing out left and right, they would cancel, and overall it would be nonpolar, but that's not our shape, so we can't have cancellation. And then 2 more, sulfur tetrafluoride. This is our extra lone pair on our sulfur atom itself. This was 34 valence electrons. So we have 32 plus 2 is 34. This shape, you need to visualize it. It's not tetrahedral. So where do the chlorines take place? Where are they? Use your words, yeah. Give me that vocabulary.
2 of them are on the equatorial, 2 of them are.
Okay, so 2 equatorial, 2 axial. What else is on equatorial? Lone pair. If you start to have expanded octet, you need to think equator and axial, because that's going to help you see where the bond angles are. So I've drawn that looking like a tetrahedron, right? But what we really are going to start to see is that the sulfur lets a chlorine go up to the side, I'm going to let a chlorine go back, a chlorine goes up, and a chlorine comes down. And then there's this extra space here, which is coming out of the board, where a lone pair is. So, one second, Alvin. So in this structure, I have this like triangle, which is my equator, or equatorial, and then I have a top and bottom, which is my axial. And so I have a bond angle that exists in the middle of what? Approximately. Okay, so we want to say chlorine to lone pair is 120. Okay, we're going to modify that in a second, but it's supposed to be approximately 120, and then on the top, 90, so that's a certain, pretty certain we're 90 there. But then you have to consider, we have this lone pair, right? This lone pair is humongous, huge. What's it likely doing to the equator, to the other atoms? Pushing them a little bit. So look on your sheet, highlight this one, because yesterday I let you guys kind of go with what you saw. You said 120 and 90. You'll notice it says for seesaw. This is the seesaw shape. If you turn it on its side, it would seesaw back and forth. This is a little hair less than 90, little hair less than 120. Right? That's what it says? Yeah. So if you say 90 and 120, I think they'll give you credit, but there's not always a guide to, hey, they get credit for this and they don't get credit for this. So and this is from AP Chem, College Board. So I'm sticking with lone pair, repels, 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 repels. So there's going to be a hair less than what our angles should have been. Okay, so almost no one saw that as seesaw at first. Consider equatorial and axial. I think you'll get better with it. Questions here? Yay, nay? Nay? Okay, so then if it's seesaw, think of your legs. Stand up. Stand up. Your legs are seesaw. Your legs are the bottom part of the seesaw. Your arms, okay, kind of back and forth. What's your head? Lone pair, okay. Polar, not polar. Why? Okay, your head is a huge lone pair. Huge lone pair. Are there cancellation of my dipoles pointing outward? No, because they're not straight across. They're angled. Are there cancellation of these dipoles? No. Okay, so 100% polar because we have an unequal distribution of electrons. Thank you. All right, so that's where I'll stop for now. I'm going to do the Socrates quiz at the end. I'm not ready for Socrates right now, but you guys will have your Socrates quiz today if I can. Okay, so let's pause on homework. Atomic orbital theory. You did your reading last night. On your 5 things you learned. Start with this one. Okay, so there are things called sigma bonds. They're just single bonds. Thank you, Daria. Okay, so lots of big words about different theory types and how we're extending what we know with the localized electron theory, which is more like the vector theory. We're basically taking our vector theory and seeing where does it fit. It fits 90% of the time. It's telling so much. But there's exceptions that we observe, and we're like, well, it doesn't fit the vector theory. Come up with another theory to explain that, which is the valence bond theory. We're going to jump into that. Jacob's yours.
Pi bonds never occur without a sigma bond first.
Right, so pi bonds build on top of single bonds. So basically, pi bonds are doubles and triple bonds. They build on top of single bonds. So we'll talk about that some more. Orishi's area? So hybridized orbitals or blended orbitals. Jack?
Electrons are attracted to low energy.
Okay, so you're talking molecular orbital. We're going to do molecular orbital theory tomorrow. Because we're going to really get atomic orbital theory established today, and we'll do molecular orbital theory. As you know, theories occur because we see anomalies in our data. And we're like, we can't explain that. We can't come up with a theory to explain that. And so that's what all these new theories are supposed to be explaining to us, to give us some context to why there are patterns in behavior in atoms, and why their behavior, or why shapes take the shapes they take, and why electrons can move in some places but not in others. So it gives us a lot of information. So I'm going to finish. We did bonding stuff yesterday. Let me go to my piece from here. Okay, so here are the two theories we're speaking of. I will go ahead and tell you, I printed a couple of these notes in your packet. Things page it's like 5 pages back in your packet. Because I know you're going to be drawing a mad woman today with me. So some of the notes, 1, 2, 3, lie 4 pages back. And I left some space below there for you. So we're really talking about the part where it says atomic orbital theory. It's about halfway down the first little quadrant. So 4 pages back. Is that simple? Can you guys point this out to each other so I don't have to break down to everybody? So I printed out some of the basics there, and molecular orbital theory there as well. That's going to be more for tomorrow. Don't be coughing on people if we just trying to get people sick. Okay, so these theories give us some insight into why the vector theory doesn't cover everything, and gives us some information about something called SP, SP2, SP3, SP3D, SP3D2 hybridized orbitals. And this explains a lot about how data is seen from an atomic level, okay? So we're talking about the localized or the hybridized electron model first. Tomorrow we'll do the delocalized one, and I'll give you guys more information here. But I'm going to start with an answer. I'm giving you the answers to everything first. Then we're going to back up and explain the answers. We're going to try that and see how it works today, okay? So, explaining the answers to you first, okay? First off, basic information. Write this down for yourself if you need to, because I do think that you guys need to write down some stuff today. What kind of electrons are involved in bonding? Shout it out.
Valence.
Valence electrons, right? Why not the inside? Okay, so the nucleus is tracking all of them, right? Because they're so close to the nucleus. They're not involved in bonding. How the heck does a bond form? What is a bond? Okay, so sharing is totally ironic. We're in the covalent world, so stick with covalent for me. We know it's sharing. Come here. Come here, please. Okay. Oh. Okay, so hold out your valence. So he's got 7 valence electrons. I have 7 valence electrons. Where are our valence electrons? Let's say he's chlorine and alkaline. Where are our valence electrons? What kind of orbitals? That's not it, though. Third energy level, but what kind of orbitals? Follow me. 3s, 2, 3p5. How many valence electrons does chlorine have? 7. Where are all of them? 3s and 3p's. Okay, so we got this like circular s orbital we're dealing with, and then like the dumbbell p orbitals we're dealing with. So imagine us like that. How do we share electrons? We overlap. Okay, that's it. I put an orbital in his space, he puts an orbital in my space, we overlap. So that we have a shared space where electrons exist, they coexist together. I'm not like throwing them to him and taking them, but where are we overlapping? What orbitals are we overlapping? So it kind of looks like P, right? But why not S? I mean, I have S valence electrons and he does too. Okay, what if I told you that all of the bonds of, if I had 4 bonds around me, they're all exactly the same size, same shape, and same strength? That means that we have to have reconsider how do our orbitals overlap. We want to say S's overlap, but they're spheres, and the P orbitals overlap, but they're dumbbells, but I'm telling you they're all identical. So that's where we start talking about the hybrid nature of this, the blending nature of orbitals. So let's talk about carbon specifically. I did an example with chlorine, but let's talk about carbon. What's the valence shell of carbon? Give me the electron configuration.
2s, 2.
Okay, so we have s orbital and p orbitals that are present in the valence shell. Okay, how many bonds would you need to make methane? What's the formula of methane? CH4. So draw methane out. There's 8 electrons here. Okay, I've drawn them all 4 the same, just like we always do. But what do I have available for bonding? I have, draw the orbital diagram out for this. What goes in the first right here? Let's just pretend we're at, where am I at? Carbon, back to, okay guys, here's helium right here. Okay, so this is 2s, 2. What's next?
2p.
So this is 2p, and then how do I fill a 2? 1 and 1, okay. So I have s spherical orbitals and then 2 dumbbell orbitals, and I'm making 4 equivalent bonds. So that's how we're seeing this discontinuity between how we've always explained orbitals and then how we're drawing them and how we're trying to visualize them bonding together. So we have to reconsider that, and that's what these new theories are kind of giving us the information to do. So it would require 4 bonds. But when you say 4 bonds, you mean 4 overlaps, right? That's what Levi just demonstrated, 4 overlaps. So if you need 4 overlaps and you have s orbitals and p orbitals, what are you overlapping? S orbitals to s orbitals, p orbitals to p orbitals. So that's where we start to get confused. Because what you really have here around carbon, and draw this out for yourself right now, is you have a big blob, another big blob, another big blob, another big blob. These blobs represent orbitals. These orbitals, to me, look kind of p-ish, right? Like p long elongated, but they don't have the other side. But they do. It's a teeny little like notch. This one goes to this one. This one goes to this one. This one goes to this one. And this one goes to this one. It's a blend of an S and a P, which we call sp3. So carbon's here in the middle. Now, half the time we don't draw the little extra notch because it just gets hidden away anyway. So that's why I just drew the blobs first. So we have 4 bonds that are going to form. So let's talk about those some more. 4 bonds that are going to form. 4 bonds are going to form. That relates back to our geometries we've been speaking of. So electron group geometry, do you remember what you were saying, domains a lot? Like how many domains, electron domains exist around carbon? How many electron domains exist here? 4. Okay, so there are 4 locations where electrons exist. 4 domains where electrons exist. All right. We also call that 4 effective pairs of electrons. That's another way to phrase that, 4 effective pairs. So there's 1, 2, 3, 4 effective pairs, meaning that they are effectively engaged in bonding. They are forcing the bond to occur. All right. If I have 4 effective pairs or electron domains, how many orbitals would have to be involved in bonding? Why?
Electrons in the orbital.
Okay, so carbon was bonding with hydrogen, like we're doing for methane. There has to be 4 bonds. That's 4 different separate overlaps, right? So there's a carbon with its 4 bonds extending out. There's a hydrogen that overlaps here, a hydrogen that overlaps here, a hydrogen that overlaps here, and a hydrogen that overlaps here. What are they overlapping? Just orbitals, okay? We're going to assign letters to these two. They're overlapping orbitals because, guys, does hydrogen have p orbitals? No, it has one s1. That's it. But here's where our electrons exist, in the overlap. There's little arrows. Remember the arrows for the orbital diagrams? Hey, 2, 4, 6, 8. Those are our 4 bonds that we've drawn right here. But I'm drawing them to indicate the shapes of the orbitals. We're going to get to that in a second. So the 4 overlaps occur. And that's going to include 4 orbitals total. Right, so there's going to be 4 overlaps. There's going to be 4 orbitals overall that force that to occur. All right, so if I told you, you guys know we had s orbitals and p orbitals that are available in carbon, right? 2s2, 2p2. Those are the 2 simplest types of orbitals, but that doesn't look like either one of them. So what I'm telling you now is that everything that comes off of that carbon there, all the bond types, they're all the same shape, the same length, and the same strength. So we can't have 2 of them being p orbitals and 2 of them being s orbitals, because then we have different length strengths and shapes. So that's what we start to cause things to blend together. And that's called the hybridization or hybrid orbital theory or atomic orbital theory or valence bond theory. I don't know why there are 4 names, but it all means that they blend. So I'm going to show you what the blends look like. Who's following me? 50% right here. 50%. All right, I'm going to get you to 100. Okay, we're going to get there. So before I move on to answers, more answers, let's draw what we know. Go for it. You can draw these. Draw a 4. And organize your notes so that you're not having to go back and try to figure out what gibberish you were working with. How many valence are in carbon dioxide? We just drew methane. What's C2H4's name? Say again? Ethene. C2, right? Ethene. So 12 electrons. How'd you guys draw this one? C double bonded to C. Thank you. So what we are attempting to do is we're attempting to consider how many orbitals are overlapping in these situations and what kind of orbitals are they. Because they all have to be identical, yet we have lots of different orbitals we're going to work with, S, P, D, F. So how many orbitals are overlapping in the carbon to oxygen bond here? 2. Okay, but they're actually going to be different orbitals, I'll tell you that. We have 4 orbitals overlapping here, and then we have between this carbon bonded to all of its attachments, how many orbitals are having to overlap here? There's 3 normal orbital types, and then we'll have a 4th one that's our double bond. So we're trying to take the structure and look at it from a different perspective. That's actually going to be 4, and I'll tell you what that means in a second. All right, so if you were just to assign the electron domains that exist around each of these central atoms, how many electron domains around carbon here. 2 electron domains. Because you're looking from left to right, there are only 2 attachments, including the lone pairs. So there's no lone pairs on carbon, so there's 1 attachment, a double bond to the left, 1 attachment, a double bond to the right. How many electron domains are here? 4 electron domains. So that's where we're considering bonded pairs and lone pairs the same way, but around this central atom, we have 1, 2, 3, 4 attachments. So we have 4 electron domains. How many electron domains exist here on this carbon? 3 electron domains. Okay, and that's because there's 1, 2, 3, despite it being double bond, 3 attachments. All right, so that's what we know so far. Now we're going to talk about the hybridization, but I'm going to do that after we go through an image, a picture that helps describe these. So we have these things called atomic orbitals. S orbitals, p orbitals, d orbitals, and so forth. The atomic orbitals are going to blend together, reshape, remorph themselves to look different. So that's what this reading right here says. You need to write down some of the highlighted parts. If not, highlight them in your, did I write this out for you in your reading? In your notes? That's what I'm asking for. Basically, yeah? Look at the bottom where it says atomic orbital theory. Yeah? Okay. Highlight, underline, circle something. Okay? So we're taking covalent bonding, normal covalent bonding, where we normally do some overlapping of orbitals. We're taking the native atomic orbitals, which are things like sp, native, sp, d, and f shaped orbitals, which we know have special shapes: spherical, dumbbell, double dumbbell, flower. We're taking them and we're making hybrid orbitals, which have a different type of shape, but they're a blend. So if you have an s orbital and a p orbital come together, it's going to be like an elongated bubble, like that. That's what a circle plus a dumbbell make. It makes that. Trust me. That's what it looks like, okay? That's what they think it looks like. So these atomic orbitals that come together, s, p, d, and f, as they blend together to make hybrid orbitals, which we call something different, which I'm getting to in a second, they still have a similar energy. They still have, if you blend a 2s sphere and a 2p dumbbell, those have energy that's specific to them because they're so far away from the nucleus, right? When you blend them to whatever this shape is, they still have a similar energy because we can't have big wonky energy gaps between what we had and then what we blend, because then there would be no stabilization occurring. Because bonding, as we probably read in our reading, bonding is a energy lowering process. If not, there's no reason to bond because there's no benefit to bonding. So when 2 atoms come together, they end up being more stable together. So that's why our energy between the atomic orbitals that are blending and the hybrid orbitals that are being formed, they're similar in their energy scheme. Okay, so another fact is the number of orbitals that you form are exactly the same number of orbitals you started with. There's no like, oh, I blend and I make 1. If I have 4 atomic orbitals that come together, I'm making 4 hybrid orbitals because I still need 4 places for overlapping to occur. I can't just mesh them together. So don't think hybrid means that they come all together as 1. Think of it as they change their shape and that's it. So 4 atomic orbitals could be something like an s orbital, let's say 2s from our carbon. How many p orbitals are in p sublevel? 3. We have 3. Px, py, pz. So there's a 2s, there's a 2px. I might need some more space here, sorry. So there's a 2s, 2px, 2py, and 2pz. 1, 2, 3, 4 orbitals come together, 4 atomic orbitals. They're going to make 4 hybrid orbitals, and those 4 hybrid orbitals are called sp3 because they're a blend of 1s and 3p orbitals. We call them sp3 hybrid orbitals, and how many of them are there? 4. So I'm saying there's 4 sp3 hybrid orbitals. I'm just meshing the letters together. All right, stop asking some questions right now, and then we're going to move on. Yeah.
You said whenever they come together, they maintain the same energy. Like,
Similar.
is that the energy of one of them, or do both their energies combined?
Their energies combined. I have a picture on the next slide that will help with that. Yeah.
So whenever several
Yes. Yes. Because we're not wiping out orbitals. We still need them to bond. We're just making them look different. Okay. So the type of hybrid orbital depends on the atomic orbitals mix. That's why I said if I blend, stop playing right now, guys. Okay. If I blend an S, a P, and a P, I blend to make an sp3, which is me adding P together to make P3. Okay. So that's what this right here is. The rest of this. So what it means by non-equivalent orbitals in the same atom combine, that means like the S, which is non-equivalent to P, will combine, which is what the hybrid over here is. Yeah.
For somebody are those all P orbitals coming off carbon?
These are sp3 orbitals coming off carbon. This is an sp3 orbital, sp3 hybridized orbital, sp3 hybridized orbital, sp3 hybridized orbital. Hold on, let me go to the next slide. I can clarify. Preach. Okay, so as we spoke of with zinc or copper and silver, we talked about electron promotion, right? Do you remember that? Electron promotion and electron configurations. Now that was just to create a stable energy system, right? Stability is key. So when we're bonding, stability is still key, energy lowering is our goal. We can do some electron promotion only in bonding for carbon. So what's our general orbital diagram look like for carbon? SP or 2s, 2, and then 2p, 2. But what actually happens in bonding is that we need 4 orbitals with electrons in them to overlap with other orbitals from other atoms so that we can get our octet and get bonding. So what happens is there's a 2s electron promotion to 2p. So we drop one of those out of 2s and we put it in 2p, so we have 4 orbitals that are half filled. So then when they bond with something else, they have octet. Does that make sense so far? Okay, so that's our reasoning for it. So what we do is when we take our electron and promote it, now we can blend, that's supposed to be blending the 2s, 2px, 2py, 2pz, we blend them together and make 4 equal energy sp3 hybrid orbitals. Because really, 2s and 2p don't have the same energy. I think my actual picture's on the next slide. I'm going to come right back to this. Here's my picture. Okay, so let me show you the picture first, and I think this will make more sense. Here's your 2s orbital, right? Here's your 2p's, 1, 2, 3. And so there is an energy difference there because 2s does nuclear penetration, so it's got lower energy. So when I take the 2s and 2p and I blend them, I make this weird lobe orbital, but they're in an intermediate energy, so they're still similar in energy. And that's kind of what that one point was to talk about the energy lowering process. But these are called sp3 hybrids. Okay? And that's what they look like, supposedly. And that's kind of what I've drawn over here, coming off of this carbon. Let me go back to the previous slide, okay? So this image, does that help? DNA? And this is the same thing, electron promotion, creating hybrid orbitals. All right, so back here, the reason that we're even talking about this is because we've seen in data collections of labs that we have 4 identical bonds. So you can't have separate S and separate P's because then we have different bond types. So that's why the 4 atomic orbitals S, P, P, and P hybridize into 4 sp3 orbital types. So that's what all this information here is. I'm going to let you read this for now, and I'm going to take some questions. Alan?
With a hybrid orbital, you have to fill up at least one arrow in each orbital.
There has to be at least one electron in an orbital that you want to hybridize. We're going to get to some examples where not all the orbitals hybridize. Yeah.
So can it depend, like, the sp3, can it, like, depend? Can you get that straight off of the number of valence electrons, or do you have to consider?
You have to consider how they bond. So I'm making 4 bonds because I needed 4 bonds, right? I had 4 electron domains. I need 4 orbitals. Those babies are going to blend. I'm going to make an sp3 hybridized orbital. But some of the other examples, we only had 3 electron domains. Do I need all 4 to hybridize? No, I only need 3 orbitals to hybridize. The other one can go and do whatever it wants to, like double bonding or triple bonding, which we're getting to next. Okay? So we assume that these things are reconfigured to create a stable situation for the molecule as a whole. That's why we're blending these to keep the energy component there so that we have the minimum energy for that molecule. Just remember, energy is probably the most important part of this whole theory. Yeah?
How do all of your orbitals have the same energy if your s orbital to start with is filled and your p orbitals aren't?
Because we promoted one of the s electrons to a p orbital, and so the theory is that when they dump their electrons in 4 different orbitals, they blend to change, they morph their shape of the orbitals, and they're all the same distance away from the nucleus, so they have the same energy profile.
Does not take energy and take
Possibly, but we're talking about distances that are minute. And when they reestablish, like, because the p orbitals, as you saw on my picture here, the p orbitals drop back down to a lower energy, while the s goes up to a higher energy, so it's a wash. That's why it's the same energy. Okay, so let's look at another style of these morphed orbitals. This is the same information. Let me just make sure, valence electrons. Oh, okay, so this is actually, we finishing up methane for you, and then we're going to go to carbon dioxide. So what we did was, and I already drew this over here for you. If you've not drawn this, make sure you do. We have carbon that came. It had its, what kind of hybridized orbitals here? What hybridized? This is sp3 hybridized, sp3 hybridized, sp3 hybridized, sp3 hybridized. Okay, I had 4 of those. And then hydrogen comes in and bonds. Did hydrogen have to change up its structure? How many bonds is each hydrogen making? 1. It's making 1 bond. It doesn't have to hybridize anything, plus it only has 1 electron. It has 1 orbital type. It does not going to promote to p blot. That's it. That's why I maintain its what shape here? Spherical. So it's s orbital is overlapping. Its s orbital all the way around is overlapping with carbon's what orbital? sp3 hybridized orbitals. To overlap to create a bond. Yeah.
So when you say, like, if you had to assign the sp3 orbital to the little atom, you know, changes.
You would assign it to carbon. Yeah, you'd assign it to the one that needed to bond 4 times. Yeah. Oh, sorry. Keep going, AJ. You good? Yeah.
So carbon, before bonding with hydrogen, made the sp3 orbital? Why just in those?
As the hydrogens approach, they morph.
Oh, okay.
Transformers. Okay. So let's. Can I continue? And make sure you note the 4 effective pair. Anytime, and this is any structure, not just methane, any structure with 4 electron domains will hybridize as an sp3 hybrid every single time. Give me an example. Not methane.
silicon.
Can you give me a full compound?
Silicon
Silicon tetrahydride?
Yeah.
Okay, keep going. Something else. I want like 5. Let's go. I don't want all tetrahedrons, guys. Give me something that has 4 effective pair, but it's trigonal bipyramidal. I mean trigonal pyramidal. Thanks, Kurt. I'm gonna say bye now forever.
Sulfur trichloride.
Sulfur has. I think this works. Okay, I'll go with that. Sulfur trichloride, ammonia, water. That's bent, but still tetrahedral electron domain, right? Give me something else. Sulfur dibromide. That's what we just had for homework. Basically, any of those have how many electron domains? 4 electron domains, and they will create a situation where they create 4 hybrid orbitals. They can overlap. Now, maybe not. Like this, I don't know about that 4 there, there's a 3 there. Sometimes they hybridize, but they don't put an electron in it. So we'll talk about some exceptions to that as we draw. All right, so this is some more diagrams showing the same thing. There's a bubble map over there. Okay, so now we have ethene. Ethene has how many electrons? Actually, let's go back to this. Ethene has how many electron domains? You just drew this earlier. So the carbon has 3 electron domains. Okay, so it has 3 electron domains, and just like normal carbon, it has 2s2, 2p2, empty orbital, right? So we're still allowing for morphing to occur. We're still allowing for electron promotion to occur. Okay, but since it only has 3 electron domains, it's going to bond how many times? 3 times. So it's going to have 3 atomic orbitals in bonding. So it needs to hybridize how many atomic orbitals? Okay, so that's 3 hybridized orbitals. Okay. We see the kind of consistency there. I'm going to go ahead and tell you that it promotes, but still it has 1, so this will come up here, okay? 1 orbital, 2 orbital, 3 orbitals that will hybridize, leaving this last p orbital unhybridized. So it has 1, 2, 3 that are hybridized, which we blended together an S, a P, and a P, leaving one of them unhybridized. Okay? Why can't I just leave the 2s there? Will it overlap with anything? No, I'm sorry, why can't I leave the 2s2 there? It's not going to overlap with anything. That orbital is filled. It can't take on more electrons. It will not bond. So that's what we allow it to promote, because we need it to bond. Does that make sense? Allie? Because I don't need to hybridize them all. That's too much energy. It does take energy to force this process to occur. Let me finish with the examples. I think I can answer these as we go, okay? So that's why we promote. Okay, so we leave one unhybridized. We have an S, a P, and a P coming together to hybridize. So that's called sp2 hybrid, because I'm only taking 2 of the p orbitals. How many sp3 hybrids do I have? How many sp3 hybrid orbitals do I have? So, did I say 3? Sorry. How many sp2 hybrid orbitals do I have? 3, because I took 3 electron domains, notice I needed 3 atomic orbitals, I made 3 sp2 hybrid orbitals. Okay, so I got 1 extra p orbital just hanging out, right? So here we go, drawing again. Get some space on your paper, because we're going to draw this together. And I might draw some on the board, actually, for my folks at home. So, ethene, right? We're going to draw it first, and then I'll explain as we go. Carbon bonds to carbon. We're going to draw our orbitals as the lobe things, okay? So shoot carbon's little fat orbital out. You're drawing with me. Please don't make me wait on you. We got more to do here. I just need some more space, so let me start over. So carbon points its orbital out. Other carbon points its orbital out. They're overlapping. There are 2 electrons there. Okay, that's the carbon to carbon bond. Carbon shoots its other orbital out to kind of like top and bottom. Same on the other side. And what I've drawn for you so far, how many orbitals have I drawn for this carbon? 3. What hybrids are they? What style? sp2 hybrid. I'm just going to write that in there so you know that these are all sp2 hybrids. That carbon has sp2 hybridized 3 times. This carbon, same story, because they have the same problem. sp2 hybrid, sp2 hybrid, sp2 hybrid. All right, so what's still remaining that was not hybridized? What kind of orbital? A p orbital. No, the s did, okay? This one and this one all came and hybridized, leaving us with a 2p orbital that did not hybridize. What does a p orbital look like? Dumbbell. Draw a dumbbell, a huge dumbbell coming off of carbon, top and bottom. Okay? Wait, you're working with me. You're good. Okay. So I've shown all the orbitals that this carbon has and that this carbon has. All right. You guys told me ethene was C2H4 with the H's on the outsides, right? what was in the middle of our carbons? A double bond. Okay, I'm going to explain to you the double bond. So we have this orbital, the one's in the middle. We have this orbital, it's sharing, right? It's showing the overlap. That is our single bond first. This one's not bonded to anything yet. So in comes who? Hydrogen. It's overlapping with carbon. What's in this overlap? 2 electrons. Okay? One from hydrogen and one from hydrogen and one from carbon. There are 2 electrons there, 2 electrons there, 2 electrons there, 2 electrons there. So far I've only represented single bonds. The carbon single bond in the middle, the carbon single bond with hydrogen on both sides. So the only thing we've not represented yet is the double bond. So build this structure. Build it right now. Build it. Don't die. Build it with do not build it with the AP kit. Build it with a little stick figure ones. The AP kit has hybridized work, and we can't work with
Yeah, let's stop moving the orbitals after their bond.
They can still, so basically they share this space. They can rotate around hydrogen and come back and forth. They can still move back and forth.
Oh, okay, got it.
Yeah, I'm just showing you a lot of that. Yeah. It's just
Thank you so much. We're not easy.
Oh no, you can use that. So I have so Kurt has built this for me. So you see the p orbitals now on my structure. They are above the internuclear axis and below the internuclear axis. So between carbon and hydrogen, you have a straight single bond. Carbon and hydrogen, straight single bond, straight single bond, straight single bond. Those are between the internuclear axis. There's a lot of overlap there. That's a strong sigma bond, as we call it. But then above and below, we have something called a pi orbital. And that pi, which is a p orbital overlap, creates our overall double bond situation. So this p electron in carbon will overlap with the p electron in this carbon like this. They kind of just fold themselves like towards each other. Same thing on the bottom. They fold themselves towards each other. There's like an arc. Okay? They did not hybridize. They maintain their normal shape, but they try to bend towards each other to share space. And I'll show you another picture of that to give you a better idea. But what you should notice is that between the nuclei of carbon and carbon, there's a large amount of overlap. That is a stronger bond there, sigma bond. Large amount of overlap, large amount of overlap, large. This is all relative. I'm telling you, there's a good, healthy overlap there. But then there's like, there's not much overlap on the top and bottom, right? So this is a double bond, which consists of this bond here in the middle, and then collectively this bond. This bond takes place on the top and bottom, though, because that's just how the p orbitals are shaped. They can't just overlap one and not the other. So there's a top and bottom nature to that. But what we describe that as is, well, you can see here, little overlap, not so much overlap, but they go above and below the internuclear axis. That's how p orbitals overlap. Now ask your questions, yeah.
So the top one and the bottom
Count as one, because they're only sharing 2 electrons. So I've drawn them there. I could have equally drawn them down here, but I'm not going to draw them here and here, because that will look like they're, and because all you're doing is counting electrons, right? There's 2 electrons, 4 electrons. 4 electrons represents what kind of bond? Double bond. If I put 2 more down here, that would have been a triple bond, and that would be misrepresenting my structure. Questions over here? Yeah.
How come if double bond is stronger than single bond, there's more of an overlap?
So good, really good point. Double bonds are definitely stronger than single bonds, 100%. But it's because of the cumulative nature of a single bond plus a weak overlap. Because if I just look at the single bond, its strength is, let's just call it 100. And if I look at the double bond situation, it's combined 100 plus 10, doesn't matter. 110, the combined nature of that strength is still stronger than just one single bond. It's cumulative. Okay? Let's look at one more example, and then I'll do some more questions with you guys. So, here's that picture again. I think these pictures work out really well. So here's your 2s, here's your 2p's. How many orbitals hybridized? 3. So the s came, and then 2 of the p orbitals came. They hybridized in a mediocre or an intermediate energy level, and if that was our unhybridized p orbital, that was still available for overlap of a double bond. Okay, so this picture is worth more than that picture. Next and last for now, yeah.
Why don't they just hybridize all the p orbitals themselves and leave that?
Because you have to have 4 places to share. An S, there's no way, and if an S was left behind for a double bond situation, there's no way it could overlap its 2 nucleus. So instead of we leave the P. Say again?
So the reason is to free the S.
Free the S electrons from being so close to the nucleus. So they hybridize the S into the P. All right, so let's do carbon dioxide. You guys had this earlier. What was our structure? Linear with 2 lone pairs. What was our electron domain? 2 electron domains. Okay. 2 electron domains. How many overlaps have to occur between the internuclear axis? So on both sides of it. Collectively 2, right? 1 overlap from carbon on the right, 1 overlap from carbon on the left. They're overlapping with oxygens, right? Because that's what carbon dioxide is made of. But there's some pi bonding or some double bonding happening here. So we have to have 2 electron domains. That means there's 2 atomic orbitals that are going to come together and hybridize to make 2 hybrid orbitals. We will leave free the ones that don't need to hybridize. So carbon, yet again, 2s2, 2p2. Shove that electron up there for electron promotion. Okay. You take your low energy level S and 1 of your P's, those are your 2 atomic orbitals. You hybridize them, putting them in an intermediate, so between the 2 energy levels here, intermediate energy level, and we call those SP hybridized orbitals, because what orbitals came together? S and P. We call them we call them 2, because there's 2 of them, SP hybrid orbitals. Leaving us behind with what? Say again? 2p unhybridized orbitals. That's what those are going to be used for. Double bonding. Because that's the only thing that a double bond needs is an overlap on top and bottom. So, with those, yeah. Because I have in my structure, Lewis dot structure, 2 electron domains. 2 electron domains means from the central atom, there are 2 locations where electrons exist, internuclear axis-wise. However, 2 of them will also be above and below the axis because of the double bonding nature. I can elaborate more. Yeah.
So does hybridization occur before the bonding?
Before they start, they do it as they bond. They morph their shapes. And you guys know these are all theoretical, right? So we have a lot of data to support this, but we're working with trying to explain it. So as they come together and start to form their bonds, they start to morph their shapes.
So it doesn't like happen before an independent atom crash?
No, not independent. Only during bonding does this occur. Only when they are bonding. Yeah.
So does a lone pair count as
Electron domain? Yes. But it doesn't have to be hybridized. It just gets electrons plopped into it. All right, so let me show you the pictures, and then we'll go through and drawing with this. And I will wrap up with a really easy summary, but I'm showing you all the details right now. So we have our S and our P's, bring 1 S and 1 P together, form our hybrids, leave 2 of the P orbitals unhybridized because they can partake in double bonding. Double bonding. Oh, actually, I had to draw this picture first. So here's our carbon dioxide, right? Get yourself some space here. Carbon is in the middle. How many of its orbitals had to hybridize? 2. Shoot 1 out to the left, shoot 1 out to the right. These are sp hybrid orbitals. Okay? So what comes in and bonds with that? Okay, so there's an oxygen atom that's coming in. I'm going to draw it overlapping like this. There's an oxygen coming in, overlapping with this. So what's inside here? 2 electrons. 2 electrons. Is carbon at octet? No, we know that it's going to have double bonds on both sides. Okay? So I'm going to draw those double bonds in blue. So p orbitals. Let's just say I had my s orbital and I put my px orbital in that bind, in that blend. So I made my 2s hybrid. That's why I'm drawing them horizontally here. Now what are still left then? P y and p z. So I'm going to draw one up and down on my carbon. There's my py on the y-axis, and here's my pz coming out of carbon, out of the board, and then going behind carbon and behind the board. I'm trying to draw it 3D for you guys. Okay, so those are big honkin' p orbitals in the x or in the z and the y axis. Oxygen has the same ability to hybridize its own orbitals as well. It has to overlap with an orbital. It also has lone pairs out here, but it also has a p orbital that itself needs to allow for overlapping above and below the axis. So oxygen too will have a p orbital that's high, up and down. Oops, I don't need this one. And I'm going to show you guys this one interplaying with the py and this one interplaying with the pz. And there's no rhyme or reason. It could be either one, either side. So overlapping here occurs. They're sharing an electron. So how many electrons are between oxygen and carbon? 4, which is what a double bond is. How many electrons are between this oxygen and carbon? 1, 2, 3, 4. Okay? So what's happening, I'm showing you the hybridization, I'm showing you the p orbitals overlapping just where the electrons are, but truly they have to overlap on both sides, top and bottom of the internuclear axis. So, oh, I'm sorry, this structure, I didn't do the whole thing. So revise that real fast. I'm trying to do the 3D nature, so this is the outside, the one coming out of the board, and this is the one that's coming out of the board. I didn't go far enough. There you go. So I saw some confused faces. And then this one overlaps in the back, and then this one overlaps here, just because that's how the internuclear, or outside of the nuclear axis, they interplay. Pause for a moment, feel the structure. Use your flexible bottoms. Thank you, Kurt. So, how are you? So, you guys see, that's actually how it looks. Oxygen and carbon have one pi bond on the y-axis and then one on the z-axis coming out at you. Okay, so that's how our double bond system has to do. Because I think someone asked me, why is one out and why is one in? Because of the p orbitals having a certain orientation. And then what do you notice? Can you turn that? Can you switch that? Yeah. Can you rotate the axis? No, it's stuck, right? Double bonds yield no room for rotating around an axis. So normally if you just have a single bond, it'll twirl, rotate, rotate, rotate. But when you have double bonds, it locks in place, and that leaves it with special characteristics. So in this finalization of this structure, I would draw my little lone pairs out here for my oxygen. And so as a final, here, I'll take your questions. What we say about this is we say that carbon is sp hybridized. How many electron domains does oxygen have? Think back to your normal structure. How many electron domains does carbon have? 3 electron domains. How many does carbon have? 2 electron domains. And how many does this oxygen have? 3 electron domains. So if you have 2 electron domains, that leaves you with 2 free what? unhybridized p orbitals, which you can see here. If you only have 3 electron domains, what hybridization does oxygen take on? So this was sp, this was sp2, and this one's sp2. This leaves me with what? 1 free p orbital for double bonding. This leaves me with 1 free p orbital for double bonding. Do you see that it did that? Oxygen had 1 free p orbital for overlapping. Oxygen had 1 free p orbital for overlapping. The rest of these, this one is sp2 hybridized along with your lone pair areas, orbitals. Even if this is sp2 hybridized, that orbital is just a straight up orbital. It can overlap with this one. They don't have to be the same orbital type. I'm just showing you the labels now to show you that you can predict the orbital hybridization for every single thing just based on electron domains. That's it. All you do is count electron domains and you're good. Can I take your questions in our 10 minutes? You're good? Okay. So, I'm not drawing these, every single one from here on out, but we went from, what did we start with? How many effective pairs or electron domains? 4. We said 4 electron domains made what kind of hybrid? sp3. 3 electron domains made sp2. 2 electron domains made sp. And then everything that was left was just free to do double and triple bondings if we need to. Well, you can go higher. You can go to 5 electron domains. But how many orbitals are in p block? 3. So you've already exhausted that. You've blended an s, a p, a p, a p. And so if you have a 5th electron domain, you have to drop and go up to d block. So then we call that blend sp3d hybrid. Or if you have more, sp3d2 hybrid. If I add up these exponents, 1, 3, and 2, what do I get? 6 electron domains. If I add up these exponents, 5 electron domains. The hybrid is showing you the answer, or the electron domains shows you the hybrid without having to think too hard about it. So a good example of something that would be sp3d hybridized is anything that is trigonal bipyramidal. What was a good example of that? Thanks, Kurt. Phosphorus pentachloride. What's a good example of something that's octahedral in shape? Sulfur hexafluoride. Thanks, guys. Okay. And then I have one more thing to show you. Give me a thumbs up if, because a lot of these are saying just like if the lone pairs there, the shape differs, which we kind of already know, but it's still considered hybridized even if the shape is different than octahedral. When I say octahedral, you're thinking 5 or 6 electron domains, which is our electron group geometry. All right, so for the, this is, hold on. For the sigma bonds and pi bonds, okay? Is this on your paper? Yes, okay. So, and this is what I was trying to speak of as we were going through the examples. If I say sigma bond, you need to note it with that little sigma, what is that, Greek sigma? Think like statistical standard deviation, right? Okay, you guys with me? All right, so if it's a sigma bond, it's the single bond that exists between the 2 atoms, just like you would draw in a Lewis dot structure, a single bond. The pi bond is what we note that are the double bonds that are above and below the internuclear axis, and the triple bonds that are above and below the internuclear axis. So a sigma bond always is what's overlapping between the 2 nuclei. So they have a really, really strong amount of overlap. That's a strong sigma or single bond. As our example, methane had all 4 single bonds, or all 4 sigma bonds. Jacob, stand up. Go. And as you go through and start adding double and triple bonds, that's where your overlap occurred above and below. That's where you have sideways overlap, which I tried to indicate to you with your little drawings, above and below the internuclear axis. And so it's a weaker amount of overlap because it's just an insignificant amount of overlap. So it's not as strong as a sigma bond. But when you build a double bond is made up of what? A double bond is made up of a sigma to start with, and then a pi. So that's why double bonds are stronger than simply single bonds. What is a triple bond made up of? Sigma plus pi plus pi. And that cumulative nature of all those overlaps creates a stronger bond situation for a triple bond. And I think that's all I'm going to show you here. There's a lot of great stuff to read though about this. This is my example where, oh, there it is, prevents rotation. So those doubles and triple bonds, they lock that position in place. There's no swinging back and forth or rotation that can occur, which creates situations like cis and trans. When you guys did your organic back in the day, if I have chlorine up there and chlorine up there and hydrogen down here, what is that called? Cis or trans? Dichloro or ethane? Yeah, there it is. Cis are on the same side, but for opposite, for the chlorine down low, not the same structure. That's called trans dichloroethane or ethene. And that's because it locks in place. You can't rotate around the axis because the double bond exists there. Okay, I have one more example for you. With this structure, you should be able to identify what kind of hybrids would occur on each of the carbons. So let's label these carbons 1 through whatever. Where do I start labeling carbons? Why? Where's the longest chain? I mean, the longest chain this way or this way, right? Where do you prioritize? Triple bond. So you start on the right. So this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Okay? How many electron domains exist around carbon 1? 2. Carbon 1 is what hybridized? sp. 2 orbitals. 2 hybridized orbitals is sp. All right. How about this carbon? How many electron domains? 2. Again, sp. What the heck's happening to the other p's? They're helping form the triple bond, right? One's going up and down on both sides, one are going out on both sides, and they're overlapping top and bottom. Because they are free to do that. That first sigma bond is overlap of the sps, and then the 2 p orbitals that are unhybridized will stay and allow for overlap to occur. Let me finish this, hold on. So, how many electron domains around carbon 3? 4. What kind of hybridization? sp3. Are there any free p orbitals? No. Why do we need them, right? Do we have double bonds? No. All single bonds. Carbon 4. 3 electron domains. sp2. What's happening with our extra? Double bonding. To make a what kind of bond? Pi bond. Pi bond is what you call the top and bottom, okay? What's this one? sp2, because there's 3 electron domains. What's happening to the free p orbital? Pi bonding to make our double bond. That's what you need to be able to do, like that. But you won't be able to visualize it unless you drew some of my structures here. Can I take your question? Okay, cool. So now accumulate, count how many sigma bonds are there. Count how many sigma bonds are on my structure.
1.
Sigmas always form first. Pi's build on top. That's what I really need you to see. Allie? 10. There are 10 sigma bonds. Where are they? Oops, sigma. Let me erase. My sigma bonds are the start of the bond. They're the first overlap that occurs. So you have a sigma here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What I've not highlighted, those will be considered what? Pi bonds. How many pi bonds are here? 1, 2, 3. Because you need those pi bonds to do the double and triple completion past the single bond that originally formed. Whew. Okay. Do you feel a little bit better from the beginning? Okay. Yes. All right. Let me actually see what I want you to do for me. These are all great overlaps. Ooh, triple bond. Lots and lots of examples. I know. This is my Darn, we're not gonna do our quiz today. We will tomorrow. I might have to push our stuff. Alright, so what I originally had for homework is not gonna work right now. Oh, but what we didn't get to in class will work, so don't worry your pretty little heads. Pretty little heads. So if you go to my website and you go under atomic bonding, because we have to do molecular orbital theory tomorrow, and I need you to make sure you're fully comfortable with this. Under where it says AP Chem, shush, AP Chem atomic bonding simulations and with MO part 4 or 4 parts, when you click that, you're only going to look at part 3 and 4. So that's what we are going to do in class. And I want you to try to pull up the simulation, but I know for sure you guys can do the part 4 without a doubt because there's no simulation needed. So I'm showing you that right now so you guys can at least see what I need from you. Maybe. Okay, that's honors chem. What's volatile mean? Volatile. Huh? Volatile means that it vaporizes really easily. Nobody in my honors can do that either. Okay. But you're better than that, people. You're better than that. Alright, so. Alright, eyes up here. Alright, so the simulated part is going to be from here. But it might require a certain type of, like Java or software or something like that. So try that if you can, but if not, I'll have you guys do that in class because I know that my computers will work for that. And it's not too long. It's going to have you look at this from an atomic orbital and then hybridized orbital perspective, and then you draw the hybridized orbitals so that you understand what they look like and so forth. And there's a couple of questions kind of go with pi bonding and hybridization. It's nice to have the simulation in front of you though when you do that. This is a part I know you can do, for sure. Drawing these structures, and you might have to look them up if you don't remember how to do your organic. Give the Lewis dot, state the shape around each atom. You're looking at electron domains for that. Kurt, go ahead and deconstruct because we're going to leave. If anybody else has structures built, please deconstruct. So state the shape, back up here. Bond angle for anything that's CCC, CCO, and so forth. Give the hybridization of each carbon, oxygen, and nitrogen, and total the sigma and pi bonds, basically like what we just went through. And there are 8 structures. I want you to do this. This is the last part we can walk through later. So if I leave that there, you want to take a picture, make sure that you can see everything you can see, but it's on my website as well. So it's under part 4. Under part 4. I like that no one actually gets up. From afar. I'm gonna like go to the way. I'll take it. You are teaching your IMFs tomorrow, so if you need to finish up anything with that, that's on you.